We're going to solve problem number 22 from section 8.2 here. This is a sequence of the form n times sine of 10 over n, and so that's the multiplication of n times this trig function sine. And we normally, to evaluate this, we normally want to think about what each of these pieces is doing. The n part is going to infinity, and the sine of 10 over n, well, 10 over n is going to 0, as n goes to infinity, and sine of 0 is 0. And so this has the form something that's going to infinity times something that's going to 0. And so it's not entirely clear what to do with that. It feels like it might have something to do with L'Hopital's rule, and so one thing we could do here is try rewriting the problem so that it looks like a L'Hopital problem. And we know that means that we want to, instead of thinking about n times 10 over n, we want to write that as a quotient, since that's what L'Hopital's rule is all about. And so it makes it look worse in a way, but that's equivalent. So dividing by 1 over n is the same as multiplying by n. And now I can see a little more clearly that as n is going to infinity, this part's going to 0. So sine of 0 is 0, the numerator is going to 0, and 1 over n is going to 0 as n goes to infinity. So this has the form 0 over 0 as n goes to infinity, which means that L'Hopital's rule might be useful. I say might because it does depend on our ability to differentiate the top and the bottom of this. So don't forget, technically, what we're doing here is defining a new function called f of x, which is defined as the sine of 10 over x divided by 1 over x. And remember, there's this relationship between the sequence and the function. The idea is that the function is a continuous curve and goes through all real numbers x, whereas the sequence only exists for the whole number values of n. So the way our graphs look, these are dots on this curve. It's an important distinction when using L'Hopital's rule, because remember, L'Hopital's rule is about differentiation, and to take derivatives we have to have a continuous curve. We really technically can't take the derivative of something that consists of only dots. So it's a technical consideration for sure, but we definitely need to do that. And in this case, both the top and the bottom here look like things we have normal derivative rules for, and so it does look like L'Hopital's rule will be helpful. So L'Hopital's rule says that this original limit of sine of 10 over x divided by 1 over x as, oops, I already wrote n there right after saying that, to x. So as x goes to infinity, the limit of this ratio is the same as the limit of the ratio of the derivatives of the top and the bottom. So in the denominator, I have the derivative of 1 over x, which is negative 1 over x squared. And in the numerator, I have the derivative of that thing, and so the derivative of sine of something is the cosine of that thing, and then times the derivative of what's inside. So in this case, the 10 over x is inside, so I have to multiply by the chain rule the derivative of 10 over x. And so that's a calculation you can do over on the side, but that will be negative 10 over x squared. So in both those cases, I'm using the fact that an x in the denominator is really x to the minus 1 in the numerator, and I'm just applying the power rule. So now I have some cancellations. This minus 1 over x squared is canceling with this minus 1 over x squared, where we leave a factor of 10. So there's an extra factor of 10 in the numerator. The denominator times 10 is that extra term in the numerator. And so now I have to now go up. So follow me up here. Draw a line here so it's not too awful to look at. So now I know this is the limit as x goes to infinity of 10 times cosine 10 over x. And so now this is just a matter of thinking about where each thing is going, working inside out. 10 over x is going to 0, as x goes to infinity. So this is going to 0. But cosine of 0 is 1, and 10 times 1 is 10. So my final answer here is that this is equal to 10. I can draw a graph to check this, to see if I am way off base. Let me just pause. I'll get another screen open here. All right, so this slide is showing the graphs. This is y equal, I'll just write it the way that it was written in the first place. I think I will. This is a picture of the continuous curve, y equals x times cosine 10 over x. And again, it's continuous, so you see every single value of x, we have a y value, and everything is plotted. And the limit that we just calculated said that it looked like the limit of this thing was going to 10. In other words, as x goes out to the right, the y's get close to 10, and that does seem about right. 10 up there. And then when you take that conclusion and we apply it back to the dots, again, the dots, this is a graph of the sequence. So this is the sequence, n times, it's not cosine, is it? It's sine. As soon as I turn the page, I can't remember what it said. Sorry, the original problem was sine. So there we go. So this was the original question. We turned it into a continuous problem and rewrote this as a fraction so we could apply L'Hopital's rule and got that the limit as x goes to infinity of this equal 10. So that's what we figured out on the other page. And then here, this is our a sub n sequence. And so here we're saying a sub n goes to 10 as n goes to infinity. And the reason is that the theorem tells us that if the continuous function goes someplace, then all the dots on there have to go to that place. If all the points are heading towards 10, then obviously the dots have to head towards 10, because these are all points on this graph. They're just the points that come from only putting whole numbers, 1, 2, 3, 4, 4, 5, 6, 7. Only putting whole numbers into the inputs are giving us these outputs. And so wherever this is going and however this is behaving, the same thing has to happen here. And that is not true the other way around. If you only know where these dots are going, you don't really know what's happening in between. And so it may be that you have a situation where these dots look like they're going someplace and the in-between points are going kind of crazy over here. So the implication only goes in one way. As the continuous function goes, so too the dots have to go to the same place.